Okay, good morning. Thank you, Annie and Gabe, for giving me some questions to work on here. Um, First one that Annie asked was 13. Um, as I look at a big, complicated series, I kind of want to look where the n is. I do notice that the n is in the exponent. That would lead me to conclude that perhaps it's geometric. However, it's got this junk on it. Now, you can write this out. In other words, go ahead and plug in 1. If you plug in 1, you're going to get this. If you plug in 2, you plug in 2 for the ends, you get, it comes out to be x squared 18 radical 2 plus, and then you're going to plug in 3, which is 81 square root 3 over x to the third. Now, if you can, I can keep doing this, but I can't. I can tell you right now, there's not going to be a constant multiplier or constant r. However, it does have the exponents in it. The n is in the exponents, which gives me a clue. Since the n is in the exponent, that it's probably a ratio test. So I'm going to try the ratio test, which is the limit as n approaches infinity of the a sub n plus 1 term, which is x n plus 1 over, just a hint, I don't like the way this is written. I'm going to write this as, and that's n to the 1 times n to the 1/2. Oh, you can't see that, sorry. Which is n to the 3/2. So I'm going to rewrite that just so I can save some space. N to the 3/2. I'm sorry. I have to make it n plus 1. N plus 1, and then 3 to the n plus 1. Divided by the nth term, which is this one. But instead of dividing, I'm going to multiply by the reciprocal. Again, remember I rewrote that n square root n to n 3/2. So now I've divided by the reciprocal. Now what I'm going to do is line stuff up. It's hard to see them in this mess. I'm going to put the ends on first. This is usually the limiting part, the part that disappears for me. Then I'm going to do the 3's. And then I've got the x's. I don't know why I put a 2 there, that should be an n. nx over x n. Okay, I've rewritten it. That's all I've done. And let's straighten some of this out real quick. Limit as n approaches infinity of same power. So I'm going to write it like that. Times. Subtract exponents. Gives me -1. Or I can just see there's one extra 3 at the bottom. So it's 1/3. Times x. X plus 1 take away 1, and n plus 1 take away n is 1. So I've got that. And this is perfect. Remember, when we're doing ratio tests, we're creating a figmentation of an r, a ratio. Well, it is a ratio. But we're limiting out these ends. Now, if I take the limit of this part, I get infinity over infinity. But by L'Hopital's rule, I get 1 over 1, which is 1. So this whole thing becomes 1. In other words, all this work, and I have the r, is this. The question says, find the radius of convergence. Okay, so this is my arbitrary r. I'm going to look for x's that allow me to create a function, create a series, this series up here, the series that will converge. Well, it will converge as long as the r, which we just found, falls in between. We'll multiply both sides by 3. All sides by 3, excuse me. And that gives me my radius, gives me my interval of convergence. Now the radius is like, it's like a radius of a circle. Consider the diameter here to be 6, because there's a distance of 6. So my radius of convergence is equal to 3. Okay. Next question you asked was 15. Got to keep it on the paper so you can see it. There we go. Okay. Again, I'm going to tell you, I can write this out. I'm going to save time here, but I see the exponents have the n in it. That's going to give me a hint it's geometric. Now I wrote it out and I found it was not geometric. The problem is this stupid n is hanging out here, which disrupts it being geometric. But it does, because these n's are in the exponent, I'm going to hint that it's probably a ratio test. So limit, let's try it. It doesn't always work. We have other tests we can do. But limit as n approaches infinity of the n plus 1 term. So I'm putting an n plus 1 wherever I had an n. And then divide by the a sub n term, which is the term up here. But instead of dividing by a fraction, I multiply by a reciprocal. And basically I just copied that one, but I did its reciprocal. And now I'm going to line stuff up. Kind of the imperative part to solving these is I'm going to put the n plus 1 and the n on top of each other. Now I can already tell that that's going to limit to a 1, but I'm going to keep working here. Put my 5's next. Then I'm going to put my x's last. And simplify it. Again, this is going to be the only limiting part, because it's the part with the n that will disappear for me. I get 1 over 5, 1 extra 5 at the bottom, times x plus 3. Limit of this is 1. So my r is 1/5 x plus 3. Now I want the interval of convergence so I can find the radius of convergence. So my interval is the r has to be between 1 and -1. Multiply by 5. Subtract 3. Now this is a little bit more difficult to see the radius, but the distance between here and here is 10. So my radius is equal to 5. This is my interval of convergence. This is my radius of convergence. Kind of gives you a scope of how wide open is the possibilities for x. Kind of allows for errors too. Now let's talk about Gabe's question, the telescopic question. Okay. Remember I said generally you want to, first of all, I see no n in the exponents. I don't think this is geometric at all. So that kind of leaves me saying I don't want to deal with a ratio test either. That's not going to work. If you try the nth test, which I'm going to talk more about in the next sections, is if I try the nth test, The nth test says if I take the limit as n approaches infinity of the a sub n, which is this thing here, if it does not equal 0, it will diverge. However, if I take the limit of this as I approach infinity, I get 4 over infinity times infinity, which is just 0. See, my nth test is inconclusive. So it leads me to the thought maybe I should just expand this out. So I'm going to take that series and I'm just going to write it out and see what I get. So I'm going to plug in 1 and I get 4 over, give me patience here because this is not, it was 1, 5, I get 4/5 plus, plug in 2, and I probably should do this in my calculator real quick just because I'm lazy. And I can start to do this real quick. If I just typed it as, I'm typing it as a y equals function. This is the bottom part. And what I'm going to do is I'm going to write them all out all at once. So I've got that. I'm pretty sure you'll be allowed to do this on your AP test. So I'm typing it in, and what I'm going to do is I'm going to go to the table. So when I plugged in 1, I got 5 for the bottom. Now when I plug in 2, I'm going to get 45. When I plug in 3, I'm going to get 117. I think I made this hard for myself. I don't see a pattern. I'm kind of glad that I haven't made a mistake. I'm just heading in the wrong direction because I see nothing that's helping me at all here. So let's try this. Let's take that same series. Let's fold this over so I can do it on another piece. And let's look at it in an even simpler form. Let's try to write it like this. Let's write 4, 1 times 5. So that's my first term. I'm starting to not like this. Wait a minute. Wonder if I can rewrite that in AB form. Let's see what happens. I'm going to change. I don't like that fraction. It's messing me up. So let's write this. Like this. Let's see what happens. I don't know. It just looks like a lot of work. Let's see what happens. So all I'm going to do is rewrite this and then see what happens. So if I do that, I get 4 equals, patience with me here, a 4n plus 1. This is called tenacity. You stick with a problem even though you don't see the answer right away. You should see the jigsaw puzzle I'm using. It's crazy. I've never done them before. Okay, so I need to get rid of this a, so I'm going to use n is 1/4. How about negative 1/4? If n is negative 1/4, I have 4 equals 0 plus b times 4 times negative 1/4 is negative 1. Subtract 3 is negative 4. B will be negative 1. And let's pick n to be 3/4. If I do that, I get 4 equals a times 4 plus 0. A is 1. Okay, so basically what I've done is I've changed that function so that it's now Sorry, I moved it so you can't see it. I'm plugging them into here, A and B. So if I do that, I get 1 over 4n minus 3 minus 1 over 4n plus 1. The reason I'm thinking I'm doing that is I'm going to change the way things are looking because I can't. It's not making any sense to me. I tried it numerically. See, I tried it numerically. I did that, and I don't see anything. So I'm doing a little bit of algebra. I'm going to fix the way it looks. So I'm going to change this function so now it looks like this. Hopefully you can still see it. There you go. So now what I'm going to do is now I'm going to try to expand it. Done. Forgot what it started with. It's supposed to start with n is 1. So I'm going to plug in 1. If I plug in 1, I get 1 over 1 minus 1 over 5. That's my first term. Now I'm going to plug in 2. All I'm doing is writing it out now. So I'm plugging 2. If I plug in 2, I get 1 over 4. 8 subtract 3 is 5. 1/5 minus, plug in 2, I get 1 over 9. Plus, hopefully you're starting to see what happens. Plus, a little tenacity works. Now I'm going to plug in, I plugged in 1, I plugged in 2, now I'm going to plug in 3. If I plug in 3, I already know the trick. It's 1/9. Plug in 3, I get 1 over 13 plus plug in 4, I get 1 over 13 minus, plug in 4, I get 1 over 17 plus dot dot dot. Now this is called telescoping. Here's why. Watch this thing unfold. See these two? 0. See these two? 0. It's like a telescope. It's just collapsing on itself. You know, a telescope where you can, anyway, you fold it in. It's basically collapsing upon itself, and it's going to keep doing that, leaving you with only one term. The correct answer here is 1. Will you see one like that? No, but it just gives you a review on how to do those integrations by parts. Okay? The AB type. All right, I'll see you guys this afternoon in the video conference at 1 o'clock.